Let's start with an ice cube. If you zoom in really far into it, you'll see vaguely cloudy blobs arranged in a neat pattern. If we zoom in on these blobs some more, we'll see that they are made up of individual tiny blobs, kind of melting together, or rather bonded together. Now, these tiny blobs are made up of a cloud, clouding around the uniform center, a center so tiny that we can't even see it from this scale, and we just have to keep going until we can see that it's not uniform at all, and is in fact made up of tiny, absolutely tiny blobs, of which we can determine two types. Now, today's video, we will start with what you get when you remove the abstraction of the blobs and enter the subatomic domain. Or in other words, so first, quarks. For quarks we have two ways to understand them, the basic way and the accurate way. The accurate way is purely mathematical, extremely advanced, completely painful, unbearably complex and mind-numbingly tough, hellishly unbearable, so yeah, we'll just use the basic one. The basic one is, we have up quarks and down quarks, and they make up protons and neutrons like this. Okay, that's it's a bit short, I promised. Bigger video on elementary particles, so fine, advanced way it is, I guess. Our story begins with scientists discovering a proton and a neutron. A pretty big discovery, I would say. Quite fun, and all scientists get excited. I mean, huge breakthrough of a decade or century. We'll never get another particle like... Oh my goodness, another particle, a lambda baryon, that's incredible! Definitely a breakthrough of the decade. We'll never get another particle like an omega baryon, an Xi baryon, that's incredible, what a break! Oh, would you look at that? They can be the charmed bottom or top, that's and they can also be like prime? I'm sorry, what? Why are there so many particles? That was the point at which scientists realized that it's a bit suspicious that we have so many particles lying around, and so we needed some way to organize them better. In the words of Willis Lamb, a Nobel Prize winner, the finder of a new elementary particle used to be rewarded by a Nobel Prize, but such a discovery now ought to be punishable by a $10,000 fine. And now some of you might be confused. Wait a second, MAKiT, none of the particles you mentioned so far are elementary, and that's because this is in the good old days when we thought they were elementary. But since there were this many of them, some scientists had a scandalous thought. Maybe they're not elementary. Alright, so first imagine a 3D space. Except you don't need to imagine it because I put it right there on your screen, right there. You're welcome! Now in this case, this free space won't correspond to position, only quarkness. So right here we have an up quark, a down quark, and a strange quark. This may seem a bit confusing at first, but it's a pretty standard way to describe things in mathematics. For example, if you've got a fruit basket with oranges, apples, and bananas, then you can describe it as a 3D space where these are apples, these are oranges, and these are bananas. Now each point in this space will describe a different combination of the three. Right here 5 apples, 3 oranges and 1 banana, right here 7 bananas, and right here 1 of each. Now the same thing we're doing for our quarks. Each point describes a different combination of the up, down and strange. Each of these points is just a vector, with these precise 3 coordinates, the upness, the downness and the strangeness. In this case, the up and down do not refer to the position, only its name of the quark. It might as well have been called red and green, or squishy and rigid, or subscribed and like, there's no difference, it's just the name. Now since each point right here is a vector, we can apply a matrix to it, so basically we can transform it in some way. For example, we can rotate a vector like this, there. And actually, due to how quantum mechanics functions, we can only rotate this vector. Any matrix transform that scales it, moves it, isn't allowed. The reason why is that's just how quantum mechanics works. This is called flavor rotation for this exact reason, and that's how we can change our quarkness around. Now, this matrix can have imaginary numbers in it. Don't even ask, okay? And thus, if we were to graph every single possible matrix, we'd have to do it in 18 dimensions. Now, this might seem terrifying if you haven't seen my Let's Do Physics in 7 Dimensions video, but in reality it's simple. It just means that we need 18 numbers, which makes sense. We have 9 numbers in our 3x3 matrix, and each one can be either real or imaginary, so times 2, so 18. The trick comes in the fact, however, that we can only rotate them. And the basic idea is, since we know that this matrix has to be this kind exactly, that lowers down the amount of dimensions from 18 to 8. Okay, I should probably explain. The basic idea is actually extremely simple. Really, genuinely extremely simple. Imagine a 3D space again. Now, each point on this space has 3 coordinates, x, y, z. So if we want to describe any point in 3 dimensions, we need to use 3 numbers. However, if we say that our points have to satisfy the equality of x equals y equals z, then we only get this line. So that way, by adding some additional information, we've just simplified our points from requiring 3 dimensions to only needing 1. That's because now we can just describe each point by the distance from the origin. So if we say that we want a point which distance from the origin is equal to 5, then we get an infinite amount of them. That's because each point on this sphere is 5 units away from the origin. If you'd like to select only one point, not an infinite amount of them, you need 3 variables. It's x coordinate, y coordinate, and z coordinate. If, however, we say that we want a point that's 5 units away from the origin, and we want x equals y equals z, then we only get 1 point. That's because, geometrically speaking, we want a point that's on this sphere and this line. That's how you can remove potential dimensions by just specifying. This is 3-dimensional, but if we add a constraint in the form of the equation, it becomes 1-dimensional because only 1 line of numbers is allowed. The same thing happens with our matrices, except instead of going from 3 to 1, we're going from 18 to 8. The reason being really difficult to explain. I'm not a mathematician, nor a physicist, so I am oversimplifying a fair bit here, but the idea is that it just so happens that we have our 8 particles called baryons: proton, neutron, 3 sigma, 2 xi, and 1 lambda. And this way of describing these baryons actually happen to make a lot of sense. Now, from what I've provided you so far, you're probably extremely confused, which makes sense because I haven't explained it all that well, and the reason why is because the sources I'm using say shit like, we attempt once more, as in the global symmetry scheme, to treat the 8 known baryons as a supermultiplet degenerate in the limit of a certain symmetry but split into isotopic spin multiplets by a symmetry breaking term. So yeah, let's just say that this is a tad difficult, but the basic idea is we have these 8 particles, scientists come up with a theory of quarks and a way they can be combined, and it turns out that this theory predicted the particles they would create. I've already covered this before, but what it basically means is that at this point we didn't really know if quarks existed. All we knew is a theory of quarks predicted reality really well. And if we fast track to modern times, then we realize that in order to describe all baryons perfectly, we need 6 quarks: up, down, strange, charm, top, and bottom. Up and down are the lightest. Strange is next in line. They are all in order from 2.2 mega electron volts divided by the speed of light squared, 4.7, and 95. And yes, mega electron volts divided by the speed of light squared really is a unit of mass, and actually it kind of makes sense to measure it this way. As one really high man once said, E equals mc squared, so E divided by c squared equals m. Electron volts are a measure of energy, so yeah, it should make sense. Then charm, bottom, and top have 1, 4, and 172 giga electron volts, which is a lot more. Actually, a quick side note, the reason why we use hadron colliders and why these gosh dang scientists just keep making new ones is because these are elementary particles, so you can't really deduce their properties. That's why the only way to actually know a mass of a particle is to measure it. So we just have to keep measuring it to get the mass, and considering how they're elementary, really tiny, it's really difficult, and we need a new hadron collider. Side note aside, these are the quarks. We can divide them by mass using 3 generations. So first generation, second generation, third generation, or there is another division, the charge division, the positive top quarks and negative bottom quarks. So I'm skipping a couple of boring values like spin, isospin, hypercharge, strangeness, and so on and so forth. There is one last thing to mention, which is really important for quarks, since all of them have a Kohler charge. Every now and then in science you will find a beautiful thing, something for which you can tell that the scientists working on it try really hard to make it understandable, something which clearly took a lot of time and effort to think of, something truly beautiful. And that something is exactly not spin! That color charge, on the other hand, is phenomenal. Basic idea is, quarks have color, red, green or blue. Anti-quarks have anti-red, anti-green and anti-blue. Now when we combine two colors together in real life, we get a new color. So red and blue give us purple. If we mix red, green and blue together, however, they all collectively cancel each other out, resulting in white or colorless. The same thing goes if we combine anti-colors with colors, so red with anti-red or blue with anti-blue. A color and anti-color give us a meson, 3 colors give us a baryon, and 3 anti-colors give us an anti-baryon. Now since we're doing physics, quarks obviously won't just stick together, so this is one of these fundamental forces guiding our universe. And in that video, I've actually explained all of them except for the strong one. So here's how it works. We have gluons. Gluons are the carrier particle of the strong interaction, and they can actually have their own color charge. Whilst quarks have 3 possible colors, anti having the other 3, gluons carry between them. So they have 2 colors, which means 9 possibilities. Oh no, sorry, the answer was obviously not 9. Why would you think it's 9? The answer obviously was 8. That's because the colors are equivalent to Glenn-Mann matrices, or in other words, the 8 matrices from the previous thing with the Lie groups and unitary matrices. So as a recap, we have 6 quarks and a gluon. Each of these quarks can have one of these 3 colors, and each gluon can have one of 8. These quarks make up hadrons, and gluons glue them together. Depending on how we mix and match different quarks, we'll create different hadrons. For example, up, up, down, proton, up, down, neutron, up, down, strange, lambda, up, strange, sigma, up, strange, xi, strange, charm, charmed omega, and so on, so forth. That's it for quarks. Quarks being elementary particles, most importantly defined by their interaction with the strong interaction. But what about those that don't interact with it? Well, that's a whole other story, and that story goes something like this. Can you see it? I'll give you a second. Well, I'm talking about the thing that you can see right now. It's obviously light. Yes, this is the electromagnetism segment, and I always like to start talking about electromagnetism by mentioning light. That's because when people think of electromagnetism, they think of magnets repelling each other, or electricity flowing through our cables, but the carrier particles of electromagnetism are photons. Pin that into our elementary bingo card. These photons are carrier particles of electromagnetism, which means that they give rise to the electromagnetic interaction, so same repel, opposites attract daily. Like the positive quarks, or negative quarks, or electrons, or muons, or tauons. It's a lot of things actually! But we've already discussed quarks, so let's move on to the other ones. Leptons. Leptons differ from quarks in 2 major ways. First one is that leptons don't have a color charge, meaning that they do not interact with the strong interaction. That's the classic difference. But another one I'd like to focus on is that quarks blur the line between a concept and a thing. You see, we made up quarks as a concept and we haven't been proven wrong yet. We definitely detect behavior, which is to be expected if quarks are a thing, but their entire origin stems as an explanation to mostly hadrons, rather than us observing them. Leptons are different, and in order to see that difference, we need to go no further than electron. The famous one. Yeah, that's the one responsible for electricity in your outlet, or reactions of chemistry, or atoms. Well, not quite atoms, more like effects of atoms. So you know, tables, chairs, apples, humans, internet, stars, iron, Patreon, cookies, waters, acid, making of Patreon, cars, houses, cucumbers, MAKiTs, Patreon. On Patreon you can support me because I'm struggling financially. YouTube's ad revenue isn't actually enough to pay the bill, so I'm slowly going downhill and burning through my savings in an inevitable spiral to lose money. Glass. That's because electrons are the most reactive part of an atom. When chemical reactions happen, it's the electrons that bounce around and cause all the fun things to happen. For example, okay, I won't spend too much time on why chemical reactions happen because I've already explained it twice, but the basic idea is we have electrons. These electrons can be in different states, or orbitals to be more precise. These orbitals specify the coordinates of electron. Now, coordinates is in quotes because it's not really there to represent its position. That kind of loses its meaning in the quantum world, especially when you're talking about the electron. Only its quantum numbers, from which we can get the energy of an electron. You can think about it this way. We have our electrons that are kind of like clouds. These clouds can have certain discrete number of shapes and sizes. Some of these shapes and sizes require less energy than others, but because it is discrete, electrons can be forced to have higher energy sizes because of other electrons or whatever. Kind of like having a ball on different shelves. The zero energy state is the ball on the floor because there is no further down for it to fall. Our ball would prefer to be on the floor since if it's on a shelf it can fall, so a ball on a shelf will fall onto the floor, but that's only if it can from that shelf roll. So if we force our ball to not be on the floor, it will not fall and nowhere will it go, resulting in high amount of potential energy. But that's all an analogy. In chemistry, an example I always like to go for is hydrogen and oxygen gas. This is kind of like our ball on the shelf. Now if we ignite those gases, then that's kind of like us pushing the ball on the shelf, and the resulting water is kind of like the ground. Well, okay, to be more accurate, it would be like another shelf, but that's beside the point. From this, we can also realize what fire is. That's because when we perform our chemical reaction, we're not really pushing a ball into an empty room, only a room filled with other balls. So as this ball falls, it pushes other balls around, resulting in a lot of movement. This movement is heat. But fire isn't just heat. You see, electrons have electromagnetic charge. This allows them to interact with the electromagnetic field, and by extent, the carrier particle of the electromagnetic field, the photon. That's why if an electron is in an excited state, so a state with a lot of energy, it really wants to get rid of that energy. And the only problem being that energy can't just disappear into the ether, so instead this electron will emit a photon. This is of course an oversimplification, but that's why fire is bright and LEDs walk. Electrons aren't the only thing that has charge, but they are extremely light. Electricity basically means moving stuff using the electric field, which isn't difficult by itself, but quarks are more strongly affected by the color charge, muon and tau are unstable and heavier, neutrinos don't have charge, bosons are carrier particles, and Higgs is... So yeah, that's why electrons are used to carry electricity. They are just the best particle out there for it. The point is, electrons are responsible for practically everything. And I do mean practically everything. That's why it is the elementary particle everyone knows about, but not that many people have heard about the cousins of the electron. Muon and tauon, they are just like the electron except less stable and more massive. Muon being over 100 times more massive than an electron, tauon being over 1000. And alright, they are more unstable, more massive, but other than that, what's the actual difference between them? Well, there really isn't much of a difference. They are so similar, in fact, that you can create muonic atoms. And yeah, this is exactly what it sounds like. In atoms, you have the nucleus made up of protons and neutrons held together by the strong interaction, with an electron floating around it, held to the atom by a much weaker but still strong electromagnetic interaction. In muonic atoms, however, instead of these electrons, you have muons. That's really it. Now, since muons are much more massive, these atoms are different in some pretty major ways. For example, they are smaller. Or for another example, muonic helium is actually fairly reactive, unlike its classical counterpart, and so on and so forth. After that we have tauon, or tau, and the trend continues. Basically, tauons are to muons what muons are to electrons. They are more massive, decay to them, and yes, they can form atoms. Honestly, the more you read about the tau, the more and more it looks like scientists are just pulling your leg and making fun of all of us. Like, for example, tau can decay into hadrons, for example, 3 pions, so you know, kind of like 6 quarks if you disregard the strong interaction, which you really shouldn't, and I don't want to gloss over that fact, but I'm kind of forced to at this point because there is so much more. Oh, you mean to tell me that a tauon can come together with an anti-tauon and can just create an exotic atom? Oh, their annihilation rates are dependent on the wave function. That kind of makes sense, but don't worry, that's not too complex. The research on that was made whole 2 years ago. Wait, 2 photons can come together and create 2 tau? Thank you so much, home.cern/news, for writing about this less than a year ago. So yeah, I know that you're probably extremely confused, but that's mostly due to 2 reasons. First of all, believe it or not, this is a weekly upload for me. Another one is that this is unbelievably cutting-edge research, and that's kind of the whole point of me flashing these sources on your screen. I really want you to appreciate the fact that science isn't in the past. It's not a relic, it's still a modern thing which we still apply as much as we can. So if you ever feel like everything in the world has been discovered, all the mountains conquered, all the lakes driven, then just remember that even putting aside all the genes we've yet to manipulate, all the reactions we yet to create, all the computers we've yet to build, even in physics, we're still more in the dark than knowing. And as a perfect of an ending it would be for this video, we still have 6 more particles. So next, gauge bosons. It may seem like an odd change of pace, but you'll see why I'm jumping to them really quickly. So what are these bosons? Well, they are force carriers, and you've already met 2 of them. Gluon is for the strong interaction, photon is for electromagnetic. Now, there are 2 more gauge bosons and 2 more fundamental interactions, those being weak interaction and gravity. So obviously we have the W boson for the weak interaction and Z boson for the weak interaction. Yeah, graviton fans cry about it. I don't care about your pretend particle. Now both of these are different, but the reason why is admittedly technical, but not in a fun, extremely advanced, interesting technical, only in a boring technical way. Basically, the model we currently have demands that we use the W boson as a medium for certain aspects of the weak interaction and Z bosons for the other. Now, weak interaction is undeniably most complex and weakest of the quantum fundamental forces, but basically is responsible for decay. With all of these lovely Feynman diagrams, you can really often see the wavy line denoted as W. This W wavy line is the W boson mediating their interaction. So, what is Z for? Well, basically, a long time ago, scientists thought that decay looked like this. You have a neutron, which decays into a proton and an electron, considering how, we just saw it, we just saw the particles. There was one teensy-bitsy little problem though. That problem being the fact that this decay was kind of losing energy, momentum, and angular momentum, which would, kind of break our whole understanding of physics. So one scientist by the name of Wolfgang Pauli theorized that there might be some additional particle which carried that energy and momentum and angular momentum away. Oh, a particle with no color charge, no electromagnetic charge, which no one has ever seen, and due to how it's not interacting with the 2 most powerful interactions would be basically impossible to detect. Oh, how oh, would you look at that, we just found a neutrino. And so neutrinos were born. There is 3 of them, electron, muon and tau, and the basic idea is decay isn't magic. Well, I mean, okay, it kind of is, but it isn't complete magic, so there are certain rules governing it. And so these neutrinos exist to make sure that these rules are followed. Basically, whenever there is some kind of lepton decay, you will probably see a neutrino floating around, to preserve the lepton number, the energy, or whatever. Or actually, you won't see it. As I mentioned, neutrinos don't have charge, meaning that they can only interact with the weak interaction and gravity. The 2 weakest interactions. That's why neutrinos were so hard to detect, and that's why it's so difficult to do any research on them. And here's where we get the Z boson, because neutrinos interact with the Z boson precisely to make sure that energy, momentum, and angular momentum are conserved. And now, you can see that our square is finished. And we're almost there. Our bingo is almost complete. We're almost at the fun review chapter where hopefully everything that needs to make sense will make sense, and we'll move past all the confusing bits and side notes. But there is one more elementary particle to mention, the really often forgotten one. I'm obviously talking about the Higgs. Now, Higgs particle isn't all that important. It's only been called the God particle by, most people. Although funny enough, a lot of researchers, including Higgs, don't like that name. Probably because Higgs is an atheist and he'd prefer it was called research and hypothesis particle. But why is Higgs boson important? Well, the boson isn't quite as important as the field, and this is going to be extremely oversimplified, but just bear with me. In physics, energy equals mass. You might have heard of it, E equals mc squared. Some guy said it, I don't remember who, probably Schrödinger or Feynman. Now, the problem is that I've mentioned quite a lot in this video how different particles have mass. The only problem being that if they were to have no energy, where would this mass come from? And here's where we get the Higgs field. Basically, as energy drops to zero, electro-weak interaction breaks away into electromagnetism and weak interaction. Mass still clings to some value, and it basically gives us a lot of potential energy. Now, the reason why Higgs has been so important and such an outlier is because it's basically the last particle. In the standard model, we knew about the electrons for about as long as electricity, with their cousins having to be discovered by actively trying. Quarks blur the line between inventing and discovering. Gauge bosons stand out as our incredibly interesting way to describe their interactions, and neutrinos were basically impossible to detect, but we still tried, and we succeeded. The Higgs boson stands as a combination of all of these problems merged into one. Something so scientifically significant that the discovery didn't even happen overnight. Instead, we spent years slowly making sure that it exists, checking and rechecking to increase the probability as much as possible until we could finally add it as the last elementary particle, the 17th, completing our set. And I suppose now it would be a good time to step back and see where we end up. We can divide them by their type, most powerful interaction, generation, all of these creating the basis of everything in our lives. A combination of over a century and bleeding edge research that's still going on today. And as a cherry on top, we have the Higgs, the last piece of the puzzle. This is all elementary particles explained. Well, that was a video and a half. Well, hi there everyone, I hope you enjoyed this video, and yes, this was a weekly upload. Well, I'm uploading it 2 days late, unfortunately, because I couldn't quite get on time. This video ended up being a fair bit larger than I expected. So I would love to thank so much to all my patrons for supporting me, because I really do need that help now, and I would especially like to thank Boo Lightning, who just casually upgraded to the highest patron rank. Just no warning or nothing, just upgraded to the philanthropist highest patron rank. So yeah, that's really cool. Thank you so much, Boo. Also, I have a patron. If you'd like to join, if you'd like to try it with me, would recommend. And also, I stream every single day a series of live streams called Charity Checkouts, which we stream for charity. Right now, we're collecting money for charity Prevent Cancer Foundation, and so I would also recommend just joining in the chatting with me, having fun. Anyway, I have to go now to work on the next week's video because I'm already 2 days behind. And for now, I suppose that'll be it. Thank you everyone so much for watching, and have a great day. Bye.